Yeah, and last not least, feature clustering. So first again, the general idea is we have the feature space F again, and in that case, unsupervised data mining task. So we're not having class labels. Target is again, of course, to reduce F to a subspace again of k dimensions. And so k is again the an input parameter, sorry. And the idea now here of feature clustering is, as the name probably suggests, to cluster the features in the space of objects. So we just somehow transpose the data matrix, yeah, and take the features, the original features, as objects, and the objects, the observations, as features, and then cluster the features. Yeah. For example, using a k-partitioning algorithm, so k-means or stuff like that, giving you k clusters, and it gives you the k features that are, or k clusters of features, sorry, clusters of features, and in each cluster, the features have rather similar, or should have rather similar values in all the observations. Yeah, so that is the basic idea, and then we can just reduce the features of each cluster to the corresponding medoid or whatever. Yeah. However, the problem here is typically that we usually have much more samples than features, so that this transposed data set or data matrix has much more features than samples, yeah, than observations. So that is always or typically a problem in terms of the stability of the clustering. But yeah, that's a different story. People just do it nevertheless. So here's an example. This is an example from item-based collaborative filtering. That is typically a killer application for this feature clustering. So you see here that the original data set has as observations the different persons that rate something, yeah, and the ratings of these somethings, that are obviously movies. So the ratings of the different movies are the features. And now, if we do feature clustering, we could, for example, find out that the ratings for features 3 and 4, so the ratings for Matrix and Inception, are quite similar, not perfectly similar, but quite similar over all persons. So they should or could be merged into one cluster. So that is the idea of feature clustering. So we hope that we get k clusters like this here, yeah, so that we just merge all the features of one cluster into one new, not one new feature, one original feature, maybe the most representative one. So probably the medoid features, so to say. Yeah. So that is the basic idea, and of course, very often we need a workaround for this many feature problem, because we have, as I said before, many observations, original observations, and not so many features. And now if we transpose the whole thing, we have a lot of features. Yeah, original rows are now the columns, so we have a lot of columns, and the original columns are now the rows, and we have much more columns than rows. And to somehow deal with this problem, typically specialized feature similarity measures are applied. For example, you can use cosine similarity or person correlation coefficient for the problem of less features or many features and less observations. Yeah? So you cannot typically use Euclidean distance or the like, but use specialized similarity measures. Yeah, the algorithmic schemas should be quite clear. So you cluster the features with k-medoid clustering based on one of those feature measures here, cosine similarity, Pearson correlation, or whatever, and then select the resulting medoids to span the new data space to get the new k-dimensional feature space, the feature projection. Yeah? And for each group, for each cluster, there is only one representative feature, and obviously each feature in each cluster, or the features in each cluster, are somehow dependent on each other. They are somehow redundant. Yeah, look at this one here. So the features here are somehow redundant. Yeah, That's why they cluster together, and that's why we could get rid of them. Yeah. So of course, depending on what kind of similarity we apply, if we apply correlation, then we get correlated ones, which is also redundant ones, and if we use cosine similarity, we get the same, of course, basically. Yeah. So we get rid of especially redundant features in that case. We don't know what the irrelevance are because we are unsupervised in that case typically. It need not to be k-medoid or k-means. K-medoid is better than k-means, obviously, because we need the resulting features, of course. So we need original features from each feature cluster. But anyway, so other clustering algorithms could also be used, of course. For example, approximate clustering methods for performance reasons and stuff like that. Yeah, but typically you do that with k-medoid because partitioning algorithms tend to have these compact clusters, and you can control the number of features, the number of clusters that are output. That's why partitioning algorithms are typically used here, and that makes sense absolutely. Yeah, short discussion. The advantages is that it depends on the clustering algorithm, or depending on the clustering algorithm, it's quite efficient. And it's unsupervised, so you don't need labels. Limitations are of course also there. So the results are usually not deterministic. So partitioning clustering algorithms are not deterministic in terms of initialization, as you probably recall. Yeah, k-medoid is sensitive to the initialization, so the result is not deterministic, but okay. Representatives are usually unstable for different clustering methods and parameters. Yeah, same, more or less the same as this one here. And yeah, this method captures again pairwise correlations and pairwise dependencies and pairwise similarities among features, but not multiple dependencies. Yeah, obviously, because with a similarity measure we only compare two things. Yeah, in that case, two features. So we can only compute and measure pairwise similarities, pairwise dependencies, pairwise correlations in that case. Yeah, so but that's that's the downside, so to say. Okay, that was our part on feature selection, and that was the part for this week. Just a short summary that you somehow get the bigger picture. So we talked about especially different algorithmic schemes to find candidate subspaces. Yeah. Of course, we also talked about different measures. Yeah, but the more important point is how to define or how to compute the candidate subspaces, because we typically have a huge search space. Even if we just look for the k best ones, we still have, if we have n original dimensions, n over k, which can be quite a lot. Yeah. And we talked about different methods for this candidate selection. So we talked about forward selection, which examines each dimension separately. So we have this attribute independence and then select the k best dimensions to get the target space. Yeah, and we had this greedy selection based on information gain, chi-square statistics, and mutual information. Of course, you can think of many different other methods, supervised or unsupervised, to do that. Backward elimination tries to have the big view, so to say, the big overview, because it starts with a complete feature space and then tries to successively remove the worst dimensions. So it has always the look on the complete picture, yeah, on the complete thing. There's no real attribute independence like the forward selection. Yeah, so that is the big plus here. Yeah, we got to know different sub schemes, so to say. So greedy elimination with with distance based and model based approaches, where the subspace evaluation measures are not monotonic, and if it is monotonic, like this inconsistency measure, we can employ branch and bound search for the optimal one, yeah, for the optimum of the measurement. So greedy elimination is again a heuristic. Branch and bound is actually a search method for which gives you the optimal fit. Yeah? And last not least, we had this subspace projections. So we had these k-dimensional projections. So that is a kind of direct search in the set of k-dimensional subspaces for the best one. In that case, we had these genetic algorithms. Here, any quality measure is possible. For example, those here or those here, no problem. And we also saw lately the feature clustering idea, which is based again somehow on a pairwise examination of pairwise correlations among the features. Yeah? So you see again the big picture with the cursive dimensionality and all the things that can happen, that all those different mechanisms, different methods somehow trade off the search for the optimal thing, which has a large search space, and of course different quality measures and stuff like that. Yeah? So always keep that in mind, and always if you have to do feature selection, which is very often the case, consider that there are many different ways to do it, and you really have to carefully think about which kind of feature selection you do, and recall it is not already or very often, sometimes of course it's already learning, especially if you do the model-based things, so the wrapper methods, but very often it's pre-processing. So that is somehow part of your process from the raw data to the patterns, and it may be that you have to try out different feature selection methods, of course, in order to get the best results. So with feature selection, the feature selection method introduces new parameters, but the feature selection method itself is a kind of hyperparameter in the whole process from the raw data to the patterns. Okay, so that was my 50 cents on that, and that was all for this week. Well, first of all, sorry, I missed the last slide here. Sorry for that. So many algorithms based on different heuristics. We talked about that. Two reasons to delete features. Once again, redundancy and missing correlation to the target, which is irrelevancy. Yeah. Very often we even get approximate results that are capable of increasing the efficiency and the quality of the data mining task. So even if we don't get the optimal solution, which very many methods do, we are still fine with that. Yeah. And once again, caution, selected features need not to have a causal connection to the target variable, but both features may depend on the same mechanisms in the data space, like hidden variables and stuff like that. Yeah, and of course, different indicators are to consider in comparison of before and after the selection performance. Yeah, that's what I just said. This is just one step in the whole process, and the selection of the method needs to be optimized somehow too. Yeah, meaning that you have to play a little bit around, not only with the different learning algorithms, but also with the different feature selection algorithms. So now, but really that is the point where we stop here this week. Further readings are listed here if you want to dig into deeper here. And next week, we'll talk about feature reduction and metric learning. So far, so good. Hope you stay healthy, and all the best, and talk to you next week. See you.